Okay, so we are going to continue looking at acid-base reactions as proton transfer. And today we are going to do the calculation questions for strong acids and strong bases only. So on the Friday before, we talked about how, or reviewed from grade 11, how weak acids and bases do not dissociate 100%. So their values at dissociation or for dissociation are not always easy to figure out. So on Wednesday and Thursday, we are going to have to do ice. We are going to deal with the mathematics of weak acids and bases. So one of the problems with Arrhenius' theory of acids and bases, he was very particular. Acids have hydrogen, okay, that's the same as Bronsted-Lowry, but he said that bases had to have hydroxide as part of their ions, and as you know, that's very limiting. So once we could do experiments, then more accurate, then what we started to notice was when you have a solution, whether it's acidic or basic, it didn't matter, then there was hydrogen ions present as well as hydroxide, which didn't make sense. If something was acidic, you only really think about it being a hydrogen. If something was basic, Arrhenius would have thought of it only as hydroxide. So there had to be something else going on. And one of the things going on is the autoionization of water. So water is a part of all solutions in terms of acids and bases. They're all being dissolved in water because we treat them like ionic compounds, and ionic compounds dissolve in water. So when you have water molecules, then they can actually proton transfer with each other. So in a beaker of a solution or whatever, there would be trillions of these molecules, but we'll consider it just 2. And it doesn't really matter, but I'll make a pattern, okay? So I'll say this water molecule will be a conjugate with this hydronium, and then this water molecule will be a conjugate with hydroxide. But again, that doesn't really matter here. We'll just keep it simple. So what they noticed was, or the fact that water can be protonated, means that this water molecule has accepted a proton. So it's the base to become hydronium, which is its conjugate acid. So if this water molecule accepted a proton to be the base, that means the other water molecule on the reactant side had to donate the proton or be the acid. And then, of course, this hydroxide, you would think of that as basic. It's negative. It likes to be accepting positives. So it would be the base. So one of the things we're going to do today is calculate pH and calculate hydrogen ion concentration and hydroxide ion concentration. And our numbers, similar to the solubility unit, are very, very small, okay? So you're going to see that again. One of the other things as well that we sort of talked about on Friday, but just that seems like a long time ago, we'll remind ourselves that chemists can be lazy. When you write a dissociation equation, you can omit the water, because when we do an ice table, we're actually going to cross it out because it is a liquid. So sometimes you'll see H3O plus being the acidic ion, and sometimes you'll see H plus. So they can be used interchangeably. So pure water has a neutral pH, which we say is 7. Then the hydrogen and hydroxide ion concentrations have to be equal. If it's neutral, that makes sense. So they have a value of 1 times 10 to the negative 7. So later on, those of you that haven't taken pH, you don't even have to change because we're going to go back in a second, or haven't taken advanced functions. Maybe you've never dealt with logs yet, but you can find the inverse of log is 10. So 10 to the power of negative pH gives you 1 times 10 to the negative 7. So then when you do an equilibrium law or equilibrium expression, then we're going to follow the same procedures as before. Products over reactants. So ions would be the products, the top of our fraction. We do not include liquids in the equilibrium expression. So we are going to cross those out. So when you do the equilibrium law or the equilibrium constant for this equation, it would just be these two numbers multiplied together. So if it's a pure water pH of 7, these two multiplied together give us a reference value, which we call the equilibrium constant for the autoionization of water, or Kw. Okay, so over here, so it says Kw, so K, which is the equilibrium constant still, but why are we using W? Because we're talking about water. So it's still the same thing. Products over reactants only include aqueous. There's no gases here, but only include gases or aqueous in the expression. The coefficients are the exponents. So I think we mentioned this on the Friday before as well. When we did that, say, phosphoric acid with the 3 hydrogens, we did one at a time. So when you do these equations, you'll often find, I'm just going to go back for 1 second. What are the coefficients for everything here? 1, okay, so then the exponent is 1. So you'll see that these are, in a way, are actually a little bit more straightforward. There'll be less squares and stuff like that when we do our ice tables. So if you have the equilibrium constant for water, or Kw, then it's just the products. There's no reactants in our expression because the reactants are liquid, and we don't include those. So if you plug in the equal number, 1 times 10 to the negative 7, in for these, then you get a value of 1 times 10 to the negative 14. So this number, it says it's a reference value. Which means it would be given. You would also be actually given the formula. That is a terrible arrow. So when you have an acid or a base, then you can actually calculate the values for the other solution. So you could be given very little information and do tons and tons and tons of calculations. So for this, quiz or test or whatever you want to think of it as, you will get a lot of formulas because it doesn't really take away from you figuring out the question. Eventually, you have to write your own dissociation equations and do ice and build the correct ice table, similar to the last unit, but not today. Okay, so this is basically what I just said in words. As acids and bases are water loving, they're always dissolved in water. So there is always water present, whether you have acidic or a basic system. And so the autoionization of water is always occurring. So what that means is it looks like an acidic question, 0.5 moles per liter of hydrochloric acid, you can use this expression to calculate the hydroxide, okay? Or vice versa. So in a neutral solution, they would be equal. So that would be water. The chance of you being asked about that would be slim. It'd be more like this. In an acidic solution, you can easily figure out the hydrogen ion concentration. You would have to calculate the hydroxide. Since a neutral solution is 1 times 10 to the negative 7 moles per liter, then when you do this calculation, just like the solubility section, your number will be tiny, tiny, tiny. So what happens is you will see a lot of scientific notation. So again, if that's not your favorite, then, do your best, take a deep breath. Okay, if you don't love alligators and you want to label what it means, in an acidic solution, the hydrogen ion concentration is greater than hydroxide, but there is some there because of the autoionization of water. But this number will be less than 1 times 10 to the negative 7, so it'll be teeny tiny. And then the reverse would be true for a base. Now the hydrogen ion will be much, much less than hydroxide. Okay, so we are going to use the pH scale as a way to interpret whether solution is acidic or basic. It is a log scale, so in grade 11, all we did was talk about if you go from a pH of 2 to a pH of 1, that's one spot on the pH scale is actually a 10-fold increase in the hydrogen ion concentration, or if you went to a higher pH, it would be a decrease. And the negative sign means that the relationship is inverse. When the concentration of hydrogen is very high or very acidic, then the pH is low, and vice versa. If the concentration of hydrogen was very low, like in a base, then the pH is high. So we talk about the pH scale, which is a practical calculation. So in grade 11, we would have looked at like what's the pH of milk, what's the pH of lemons, the pH of coffee, the pH of pop, something like that. There are definitely solutions that we have locked away in our chemical storage room that can have a very, very low pH, like a negative pH. But for you to have those in your home, you would probably have to answer some questions. So even 1 molar nitric acid, we use it. Remember that lab we did with the colors? I had to dissolve it in nitric acid. That's the only time we use that acid. It has to be stored in a separate container, in a separate spot from the other acids. So we have to follow guidelines for safety so that we keep you guys safe and ourselves too, I guess. So if your pool, for example, you measure the pH of your pool or your hot tub, if the pH of that was negative, then, or the pH of the coffee you were drinking was negative, you would have some problems, right? So when you get a negative answer for pH, it's not that you're wrong. It just means you have a very, very, very strong acidic solution, okay? So this box means that you're going to get these formulas. So those of you that would have taken advanced functions should have studied logs. So if you have a decent calculator, your calculator should have a log button. It needs to be in degrees. So if it accidentally has gone to radians, then you need to change it. Or if you were in advanced functions and then you were done the trig unit, you would have to make sure it's in degrees. Most good calculators will have a button that is like second function or the shift. The inverse of log is 10 to the power of. So you can do this as, you can type it in as 10. This means to the power of negative pH. However you do that on your calculator, or you can do inverse log. It'll do the 10 for you and it will raise it to the power and you just have to put in the negative pH. It is not multiply. It is just negative log and then the hydrogen ion concentration. So if you don't have experience with logs on your calculator, then this homework is pretty straightforward. Just you do the homework so that you get practice, because tomorrow and Thursday we are going to do ice tables. So we're going to, it'll just be a little bit more work. pH means the power of the hydrogen ion. So again, acids were just more studied. So we have a scale we use the pH scale to interpret whether a solution is acidic or basic. You can also calculate pOH, but when you get a base, then you'll always have an extra step. So you can do the same sort of thing for a basic solution as well. pOH is negative log of the hydroxide ion concentration. If you need the hydroxide ion concentration, it's 10 to the power of negative pH. But usually the question will not, like the final answer, you'll want to interpret it like you're used to. So this will become important when you have a basic solution. You'll have an extra step where you have to change pOH into pH. Okay? But these would also all be given to you as well. Okay, so we're going to do some examples. So today, the examples we're going to do, the homework, are only for strong substances which dissociate 100%. So we will talk about in the next lesson how you can quantitatively figure out whether something is strong. this question, it happens to tell you. If it doesn't explicitly say it in the homework, just know today's homework is all strong acids and strong bases. And the reason that matters is then 100% forward, no equilibrium, so no ice. Okay? So here we have nitric acid. Really, this question is so straightforward. It probably would be out of 1 mark. You don't necessarily need the dissociation equation. However, eventually you will, so let's just practice. So what I'll do is, especially for a strong substance, students often don't write the water because, we would cross it out anyways. So you can write it 2 ways. Okay, so if you put the water in, this is an acid because it says acid. Okay, that means that water, that it's going to give away its H. And water has to be the acceptor. Yes. Nope. So yeah, let's do that one. Okay. So when you have something strong, because the question is really straightforward, there's no ice, then lots of people will just do this. Just split it apart into its 2 ions. So again, lots of our acids are oxyacids. Maybe you need, yes. Maybe you need the polyatomic ion or whatever, so you can use that from your periodic table. So this nitrate is just a polyatomic ion. The question asks us for pH, so we actually really care about the hydrogen ion concentration. So I'll talk about how to deal with the fact that it says 2.5 molar nitric acid. What does that mean? But either of these are equivalent or interchangeable because, again, let's write it down one more time. Okay, so H3O plus is the same thing as H plus. You can use it interchangeably, so either of these is fine. So in grade 11, when we did stoichiometry of solutions, we looked at a way you could sort of streamline the stoichiometry or stoichiometric process. So you can do that here. If you would prefer, you can write out full stoic ratios every time. But really, just like the water equation, what are the coefficients here in either case for everything? 1. So you're going to divide by 1, multiply by 1. It's very, very simple, very straightforward. So if the concentration given to you for the acid is 2.5, then it's the same. Okay, so there's a few ways to think about this. So the formula for pH is negative log of the hydrogen ion concentration. So that's all we need for pH. Or you can also think of other items that we've talked about. Water we would cross out. What kind of ion is nitrate? Comes to the event but doesn't participate. Yes. It's not acidic, so we don't care what it is. Would it be 2.5? Yes, but it's not going to affect the pH. So whether you write the equation like this or like this also doesn't matter. And again, practice with your calculator to see how it works. Don't forget to include the negative sign because it is an inverse relationship. I rounded it, that's no big deal. Again, a super, super low pH. If you had a solution of 2.5 molar nitric acid, you would have some explaining to do. So it is a very, very low pH, very strong acidic solution. So again, we wrote lots of stuff here because this is obviously a note, but really I would probably expect only the calculation of pH. This question would be out of 1 mark. This is very straightforward. When you get something that is strong, then you will be very happy. Makes your life way easier. So it says strong acid. Tomorrow we'll look at if it's weak, you'd be given an equilibrium constant value. But so today for all the homework, it'll just be strong. Okay? Okay, so the next question, it says to do the POH. So this is a base, barium hydroxide. So I chose barium hydroxide on purpose because when we split it apart, how many hydroxides will there be? 2. So then the coefficient will be 2. You can still streamline stoichiometry. You just have to multiply the 0.35 by 2. And again, the barium is a spectator. We're asked to find POH. So the only thing we need is OH. Sorry. So usually a question like this, we wouldn't leave the answer as POH because we're not used to using that in our interpretation, you would have to do pH plus POH equals 14 to convert it into pH. But the question says POH, so we're good, we're done. In part B, it asks us to calculate the H plus concentration. So I'm going to do that two ways. So again, every solution, even though you're used to thinking of a base just being OH and an acid just being H, because water can be protonated or ionized, then you can calculate the other ion as well. So you can do this using this. Because Kw is always 1 times 10 to the negative 14. That would be a given reference value. Okay, and then this is like your X. All you have to do is divide. So pretty straightforward, just an extra calculation. And you get a teeny weeny tiny number, which also makes sense. This is a basic solution. You wouldn't think of it as having, that's an M, sorry. You wouldn't think of it as having hydrogen ions, but now you know there is always some. I'm going to add in another way you can solve for this. My other class made fun of me because it's a little bit more work, and they were like, Ms. Todd, I'm never going to do that. But I'll show you how to do it. So when you have POH, you can change it into pH. So 14 minus POH, like you're bringing the POH value over, changing the sign. This way is not bad, even though it's a little bit extra calculations, because then it helps to confirm, oh yeah, 13.85, that's a basic pH. Some students, if you left it as POH, you know, that seems nasty. I don't like that. And then once you have the pH, then you can use the inverse log. And you get the same answer, okay? Oops, sorry, got the 0.4. Okay, so if you didn't get a chance to do the conjugate acid base pairs, try that, because tomorrow we're going to have to write dissociation equations in order to do ice. These questions, the math part of it is straightforward. There's no ice yet, so the more you're comfortable with those formulas, especially if you did not take advanced functions, then the better off you'll be tomorrow.